Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 9.8, Damped Harmonic Oscillations. We've talked about simple harmonic motions, but we have only talked about simple harmonic motion in terms of things that we idealize as of there is no friction in play. So let's get that into our equations and get some damping motion in action. There are three main types of solutions that you need to know about damped oscillations. If you've followed the entire course so far, then you would know which three types of solutions they are. However, let's see, there are some things that you need to bear in mind when doing damped oscillations, which, unlike previously, you just need to know the algebra, you now need to know their real life interpretation. So let's have a look. So let's look back to the simple harmonic oscillation equation in general form. We've got x dot dot plus omega squared x equals to 0. This is the general formula. For a damped oscillation, you would have thought, well, at least at first I did thought, that there will be something to do with the particular integral, but no, that's not the case. It's something to do with your first power dot. So you have some form of x dot we call 2 gamma x dot in the mix, which let's write that in full. X double dot plus 2 gamma x dot plus omega squared x equals to 0. And we are still having no particular integral because we're not forcing the oscillation. So if we are driving the oscillation by pushing it, like you would have done with a swing in the playground, then you would have added some component over here. Let's see, so for this one, we can solve for the auxiliary equation as we do, which gives us lambda squared plus 2 gamma lambda plus omega squared, just omega squared, and with that equal to 0. And guess what? Let's do what we do best, the quadratic equation formula. So minus b minus 2 gamma plus or minus the root of 4 gamma squared, that's b squared minus 4 lots of omega squared all over 2 times 1. So with that, we can find lambda, and turns out that this is the reason that I put 2 gamma in is such that I can cancel out the 2 right here. So we're left with minus gamma plus or minus the square root of gamma squared take omega squared. Yeah, right. So we have this expression which is kind of interesting so far. There are a few things that can occur right here, which includes first of all, if gamma is larger than omega, you get one solution. If gamma equals to omega, you get another solution. If gamma is smaller than omega, you get another solution. Right, so now we are on to the three solutions that I want to talk about. The first one, gamma is larger than omega, that would go to let's see, gamma is greater than omega, which means this square root is a positive number, which is real, which means that, as we all know, there are two real solutions. So two real solutions lead to a e to the lambda t plus b e to the lambda 2t. So separate the two lambdas with subscript 1 and 2, which is the general solution. And we can tell this is an exponential form. This is an exponential form. So we get an exponential solution. In the real life interpretation, that would also mean that because the middle term is the friction term and the omega term is the natural oscillation term, we can say that because the frictional force is so great such that you're trying to, this is one example that my prior physics teacher taught me, which is trying to swing a pendulum in, let's see, creosote oil or something. Yeah, basically the damping force is too great such that it's no longer oscillating. Instead, it's trying to return to the initial position really slowly, so you get something like that, and where this is equilibrium, of course. And if I'll just draw a few graphs over here in a bit. So this would be gamma greater than omega. For a gamma equals to omega, it would be a bit more interesting. You would get a 0 over here, so you get 2 lots of minus gamma as your solution. That, let's see, we know for double roots, so double roots, we get a solution in the form of ax plus b e to the lambda t. So this solution gives us this special x term as one of the exponent coefficients, which means that as x, well, actually this is t, isn't it? My bad. I always do that. Just bear with. As t goes to a large number, this b gets irrelevant, and so initially it involves more of this b exponent, but then as time goes on, the a exponent takes over. So basically you have some interesting curve that is not quite exponential, but it's a lot, or it's quicker to settle than the initial one, the what we call overdamped ones. So this would also give us exponential solution. However, for gamma is less than omega, we get a I value, which is a root of a negative number, which means that we have a complex solution. As we know, complex solutions gives us a cos plus b sine, and the contents within would be the gamma squared take omega squared in real form, which we can just write the square root of omega squared take gamma squared, essentially we took the I out of the equation and just stuck things in. Remember your T as well. So that would be your general solution plus, of course, the exponent term e to the minus gamma t all multiplied. So by far this gives us the most interesting / complicated general solution. And in this case we can tell, although there is an exponential form, mainly there is this sine and cosine term, which means that it is always oscillating. So this would give us an oscillation solution. And to be fair, I should have gave color to these lines really. Oops. And I'll give this, I'll draw this such that you can tell that because it's damped, it's kind of, how should I say it, it's relatively speaking, if they have the same kind of damping force, then they should decay with the same amount of time, because the decaying constant gamma is can be related to an energy loss value, which if the system start with the same energy, they should decay at the within the same time. But it also depends on the initial energy, which will change omega. It depends on the friction, which change gamma, and if these happens, then you get 3 different solutions as shown on the curve. The red line gives us the quickest delay timer, which means that it settles the fastest out of all 3 solutions, which is called critical damping. And this is very important in all forms of engineering and all forms of instrumental science applications, such as weighing a baby, for the car, don't even know what it's called, basically the spring that stops your car from shaking around. Those are all critically damped such that it doesn't keep oscillating, nor do you crash into the ground, or worse, it takes a very, very long time for you to get back to your to the comfortable configuration. For the gamma is less than omega, you get the oscillation, and it's called underdamped. And for gamma is greater than omega, we call it overdamped. And there are also something that I want to talk about for damping. There are a lot of situations when you want to say one is more damped than the other, you use it's more damped rather than it's over damped, because it means completely different things. It's less and more would give you a relationship. They can both be underdamped while one is more damped than others. But if both of them are underdamped and you decided to use the word overdamped to describe that relationship, then no, it's just plain wrong. So bear that in mind. Other than that, basically just look at the equations, solve for the solution, and then interpret if it is underdamped, overdamped, or critically damped. For this damped oscillations, it is very important that you know the graphical interpretations for a overdamped, critically damped, and underdamped situations. Some might want to remember the discriminant form such that you can just tell from the get-go that whether a particular scenario is going to be overdamped or underdamped or critically damped. However, I would just straight up calculate it, because you might as well. Most of the time they would ask you to give a solution anyway, so I personally don't find that a too important of a mathematical it's not even skill, what should I call it, basically if you want to remember it, go for it. It might save you 5 seconds, but in general I do not recommend hard remembering stuff anyway, so yeah, basically that's it. For the questions, I've got you 2 questions to carry out, and basically just find the solution, then state its nature. Nature, aka the form of oscillation, so whether it's damped, critically damped, or well, overdamped, critically damped, or underdamped. Yeah, basically that's all I want to say, so I'll give you 5 seconds to pause and do the questions, and I'll show the answer in 5, 4, 3, 2, 1. So the answer is shown right here. The first one is overdamped and second one is critically damped. It's relatively straightforward to solve for the solution, given that you've done a lot previously. And so yeah, that's all for this video. I hope you've learned something. If you have any questions to do with differential equations, do let me know in the comment section below. With that said, I hope to see you on my next one.